over, under, and through, three-pronged approach to geologic mapping of karst terrain of West Central Virginia, presented by Rose-Anna Behr and Bryan Crowel. Investigating geology in a karst terrain is our hobby, not our career. So why do we do this? It gives us a better understanding of the resources and additionally, where to look for new caves. Besides, it's fun. Burnsville Cove is located in Bath and Highland counties of Western Virginia in the Valley and Ridge Province. The area is marked by linear valleys and ridges of the Appalachian Mountains. This is a topographic map of Burnsville Cove. North is to the top right, and the scale is 2 miles total. The cove is loosely defined as the area between Jack Mountain and Tower Hill Mountain, the town of Burnsville, and the Bull Pasture Gorge and water sinks. On this bird's eye view looking northwest, the valley containing Bolar is a breached anticline or upwarp of Ordovician carbonates. This ridge is Jack Mountain, and the valley that contains the cove is a broad syncline or downwarp with multiple secondary folds and possible faults. It is underlain by Silurian to Devonian carbonates and some siliciclastics. In the foreground is Tower Hill Mountain. Note Burnsville and the Bull Pasture Gorge. There are over 100 caves and more than 72 miles of surveyed passages, with Butler Cave and Breathing Cave being an official national natural landmark. The first geologic mapping was done by Bick in 1962, and more recently, John Haynes of James Madison University, his students, Chris Sweezy of the USGS, Rick Lambert, Phil Lucas, and others have been working to improve the mapping. Colors shown here are based on rock type, with yellow being sandstone, blue is limestone, and gray-brown is shale. Note Jack's Mountain and Tower Hill Mountain, Burnsville, and the Bull Pasture Gorge and water sinks. The area of special interest to us is the Sinking Creek syncline and the Chestnut Ridge anticline. Remember, the synclines are the downwarps and the anticline is an upwarp. Now I mentioned the Tuscarora, which is Jack's Mountain. So that's Silurian sandstone. And the caves are in the upper Silurian and lower Devonian, the Tonallaway, the Kaiser, and the thin limestones above it, and the Oriskany sandstone. This group is also called the Helderberg group. This cross-section from DHO in a 1986 SEPM field trip guide shows a cross-section from south to north in Western Virginia into West Virginia. Notice the tongues of sandstone are thickest to the south and thin to the north, where they begin to interfinger with the limestones. Our area of interest is the Bull Pasture Gorge. A large, stable carbonate bank, kind of like the Bahamas today, was established at the end of the Silurian into the Devonian. Over 300 feet of limestone accumulated, and within these limestones, we now find the caves, typically constrained by those tongues of sandstone. Shown here is the human-made entrance to Butler Cave. You can see the lower breathing cave sandstone, LBCS, in the high wall. Of course, the upper breathing cave sandstone would be above that. They got their names in Breathing Cave, which formed sandwiched between the two sandstones. This entrance to Butler Cave is below the lower, and the original entrance is below the upper sandstone. Looking at a profile view of the trunk passage of Butler Cave, you'll note that the sandstones influence the cave formation. The entrance is below the lower sand, which constrains it until it punches through at the dry sumps, The cave then continues, sandwiched between the two sands. The upper sandstone is very durable, and throughout the cove, it forms ceilings or floors of caves. The lower sandstone weathers more easily, so it somewhat controls cave formation, often being observed in cave walls. Knowing we'd be hard-pressed to improve on the stratigraphy, we focused on structural interpretations of bedding orientations. With our three-pronged approach of field mapping, LiDAR observations, and in-cave observations. For traditional field work, you head out armed with a GPS, a topo map, rock hammer, camera, and notebook to look for outcrops and abundant loose rocks. We reported the rock type and measured orientation, as shown here, using a brunt and compass. Traditional field work, though rewarding, is time-intensive, especially for weekend warriors with other items on their agenda. This technique also faces several challenges. There's limited bedrock outcrops in limestone and shale valleys, so you do a lot of mapping by float, which is loose material. You also have to address landowners, ticks, snakes, bears, heat, snow, and then the data tends to be biased towards the resistant beds. Shown here is the Clifton Forge sandstone in the Kaiser Formation. Now, fieldwork remains very important to ground truth any ideas based on the LiDAR. LiDAR is a very accurate elevation model created by an airplane flying over, shooting down lasers, and timing the return. It's accurate to within 10 centimeters in a farm field and 30 centimeters in the forest. Post-processing removes trees and buildings, and amazing details are revealed. You can then process this data to get images such as this. This hillshade, which is commonly used, is illuminated from the northwest, so things on the southeast slopes are hidden. I much prefer slope shade. Steep areas are dark, flat areas are light. You can see resistant beds, such as in here, the upper and lower breathing sandstone. You also can see sinkholes and swallow holes. It's a useful tool to prioritize fieldwork, and when used in conjunction, gains the best results. LiDAR reveals that in the southern part of the cove, near the village of Burnsville, where the lower Tenalloway Formation outcrops, joints actually control topography. You'll notice beds are oriented this way, but the valleys and ridges out here are this way. It's also been noted that the joints often control the cave passages. Slope shade's also useful in exploring for caves. You can see all the sinkholes and swallow holes and plan your digs accordingly. A couple things we observed on the LiDAR in the resistant beds. You still need to field check them to find out if they're sandstone or limestone or something else. But we observed an unmapped fold on the eastern flank of Jack Mountain. Several of the folds, previously mapped or unmapped, are asymmetrical. The dips of the eastern limbs of the anticlines appear steep to vertical, whereas the western limbs are less steep. The hinge zone in the synclines is broad and flat, and second and third order folds can be seen. Textural differences in the LiDAR assist with geologic mapping. The limestone areas appear pockmarked, the shale areas appear smooth, and the sandstone forms resistant ledges, and sinkholes in it appear broad and circular and shallow. Their alignment in that area belies the joints and dissolution in the carbonate beds below the sand. Details from the LiDAR also reveal that Mill Run is not aligned with water sinks, whereas on the topographic map, they appeared to be well aligned. Also note that the northern part of the cove, the topography is controlled by the resistant beds. Shale is here and sandstone, and then the pockmarked limestone. Here's the Clifton Forge sandstone. forming a resistant fin. Now, to get the structural measurements from the LiDAR, such as the strike and dip of beds, you select a resistant bed and digitize 3 points on the bed. Calculate the northing, easting, and elevation, and you extract them to calculate strike and dip. It's your basic 3-point problem. Or if you work with the Esri ArcMap, there's a tool, and you digitize a line on a bed, and it does the rest. It can do them much faster, and it also statistically discards bad beds if you don't have a good point distribution. Field measurements tend to be on smaller planes, so one benefit of LiDAR is the ability to measure large features. A bird's eye view is a different perspective. LiDAR is not hampered by vegetation. Data can be collected over a large area, quickly, without landowner permission, or dangerous encounters. Now, the third prong of our approach was in-cave mapping. To collect within the cave, minor adjustments are needed from fieldwork. GPS units are of no use. Accurate base maps are necessary. Fortunately, those are available for the Cove based on over 50 years of exploration and surveying. There are many benefits. In an outcrop-poor valley or heavily vegetated areas, the caves offer nearly continuous outcrop. They afford a view of the internal working of the structures that only peek out at the surface. This 3D view is important to understanding the overall structures. Shown here is an anticline fold. Small faults and complex folding, easily missed in surface outcrops, are observed in the cave walls. Note the fold at the end of this small fault, accented by red beds of the lower Tenalloway limestone. Work can be done year-round in relative comfort of 51 Fahrenheit air without insects, snakes, dogs, poison ivy, all those other challenges. Though at times, the amount of outcrop is overwhelming. Now, the caves also need to be in a useful orientation across the structure, not strike parallel, for best data results. Here, the beds dip to the right, so a passage to the left or right would show you more bedding variations than a passage continuing straight on. Caves may be wet and muddy. The walls may be coated with gypsum or cave formations that cannot be disturbed, which makes collecting the geologic data difficult to impossible in these areas. Some caves require technical skills that not all geologists have, such as rope work and the ability to squeeze into small passages. Other cavers have been recruited and to date are eager to assist. They make general observations, take photographs, collect samples, and measure bedding. They use a Disto-X laser rangefinder with built-in compass and clinometer to collect the strike and dip. It's used by non-geologists since they're familiar with the tool from surveying. The Disto-X accuracy is similar to a Brunton compass. The in-cave data are biased towards the limestones in which the caves form. We amalgamated our data from the field, LiDAR, and within the cave. Purple lines are cave passages. The yellow here is the small anticline I pointed out earlier in the LiDAR. In our field mapping within the cave, we adjusted the location of the Sinking Creek syncline. In red is the data we collected in the Sinking Creek syncline. The green is data collected on Chestnut Ridge anticline by our friends. The blue are field measurements, ours and previous workers, and black is data from LiDAR. The cross section here from Jack Mountain to Tower Hill Mountain is drawn here. Overall, it is a primary syncline with noted secondary and tertiary folds. If we zoom into the Carbonate Valley, the caves can provide firm data below the surface. For example, Wowway, Barberry, and By the Road are floored by another one of our resistant sandstones. Now, Chestnut Ridge is likely more complicated than shown here. It is possibly a small fault cord anticline, and we need to do more work to resolve that. The top right is a stereo net. This graph helps us to visualize bedding measurements from over a large area. On the top right, the sketch can help you understand what's going on here. If we draw a vertical line from each bed, they then become points on the stereo nets. Then on the stereo net, we draw the circle that best falls on all those points. And the pole to that is the fold axis. The takeaway is these are the orientation of the fold axes based on our different data sets. Red is Butler, and it matches well with the blue, which is the field measurements, ours and others. The black is the LiDAR measurements and is slightly off. And then green is Chestnut Ridge, anticline, and the axis is even further off. Well, why is that? Maybe the structures in the north do something different than the structures in the south, though it is noted that field and LiDAR measurements are from all over the place. The axes are not parallel, though they formed under the same stress field. This indicates that folding may be more complex than first thought. Perhaps a model similar to Fail and Wells, 1974, kink band folding may explain these non-parallel axes, such as this may be Chestnut Ridge anticline, and this is the Sinking Creek syncline. Or perhaps the presence of unmapped faults may complicate the structures. So our conclusions are that the new LiDAR maps and additional data collecting will improve and refine the geologic structures, possibly assist in locating new caves. Our future goals are to plot the small structures separately from the large, see how they relate, of course, collect more data, especially in Chestnut Ridge. Oh, and figure out if there's a fault. We need to ground truth those LiDAR interpretations, and always, we want to discover more caves. We wish to acknowledge those individuals and organizations that made this possible, especially the Butler Cave Conservation Society, which is dedicated to the conservation, exploration, survey, preservation, and scientific study of the caves in and around the cove. If you have any questions, please feel free to contact either of us at the email addresses provided here. Thank you for your time.